As we saw in the previous lesson, network processors are embedded systems with unique issues. Without careful software design, a network processor can become overwhelmed. One area of particular interest is resolving bank conflicts. In this particular lesson, we are going to discuss the dual bank allocation problem, the conflict and no conflict law, and 3 approaches to solving the problem, and finally an odd cycle detection and breaking framework. So students, so far you have been looking at embedded processors for variety of different kinds of processing that happens, such as DSPs, ARM, VLIWs, and so on. But now we are going to focus on a totally new kind of network processor, which is a kind of embedded processor for doing a lot of processing in the network. So before we dive into the network processors and the different kind of network processing applications, let us first look at the demands of network processing applications in terms of what kind of processing happens in network. So to your surprise, network processing has a lot of demands placed on it. First of all, network processors have to deal with very high speed, that is gigabit network traffic. And then secondly, in modern networks, a lot more processing happens in network, not just forwarding of packets or routing and things like that, but a lot more processing. And these processing demands keep changing. More and more processing is needed, for example, for doing security analysis of packets and so on. And that demands a lot of programmability because new kind of processing must be put in there through software. And so finally, here is one solution that is offered by these network processors, that all these can be done through one device, and it can do a variety of different kinds of processing, not just a fixed kind of processing, which is typically the case with the hardware-oriented routers and so on, which do not offer us a functionality to keep changing the type of processing we want it to be done. Having seen roughly at a high level the kind of network processing demands that we have, now let's take a quick peek at a generic network processor. Typically what we have is a CPU interface. So this acts like a coprocessor, obviously. And we have a RISC core or cores rather, and they do a variety of different things such as pattern matching. We also have a buffering unit which takes all these input packets and buffers them and so on. And then we have a multitude of RISC processors. We carry out the processing that we write in terms of applications. We have a high-speed network interface to get all the packets in, and we store the intermediate values and results into the memory. Having seen the general demands on network processing and a generic network processor architecture, now let's kind of enumerate different demands we need to place on the network processors, which is a specialized processor which kind of meets these demands of doing very high-speed processing. So first and foremost, we must have very high performance because we must match the line speeds which are at gigabits per second. And in order to carry out this processing at that very high speed, we have a specialized processor which has a different ISA, which has a different architecture and so on. And so what are the different characteristics of this specialized hardware or specialized processor? First of all, it has to support very high amount of parallelism. So it should be based on multiprocessing. It is also based typically on multi-threading to exploit parallelism at finer levels. It also does the instruction level parallelism. So you can see it is all parallelism, 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 parallelism. And this is to facilitate as much parallelism as possible within the network processor. And then finally, to support this parallelism, we must have parallel data paths. Otherwise, all this parallelism cannot be utilized because of the bandwidth limitation. And this is the way we can bring all these packets at very high bandwidth, get them in, use all this parallelism, and deliver the processing at line speeds of gigabits per second. You might wonder why we need to have the line speed at gigabits per second. The answer is very simple. If we do not do that, we'll have to store the packets and the storage will become unbounded and the whole thing will not work. So the idea is to keep these line speed matched to the processing speeds so that the buffering is minimized. And so with that in mind, let's take a quick peek at one of the practical network processors. This was Intel's IXP 1200 family, which was later replaced by 2400 family, but the core ideas remain the same. So what we have here is again a host CPU, so this acts as a co-processing unit. We do have different ports here to bring in the data from different types of lines, which is Ethernet, ATM, and so on. And then we have several micro engines here which exploit the parallelism. As the packets are brought in, they are stored in one of the memories here, which is SDRAM, which is on-chip memory. We also have a substantial amount of SRAM, which is off-chip, and flash ROM, and so on. And then we have several micro engines which work on these packets, do their processing, and then once the processing is over, they deliver the packets on the outbound buses. So in this way, supporting a lot of parallelism is achieved in IXP 1200. It is also achieved that we are able to store these packets in different levels of memory hierarchies to minimize the latency and to maximize the throughput. Now let us continue this discussion and take a more detailed look at what is exactly there within a micro engine and what kind of processing really takes place there. So as you can see here, each of the micro engines support 4 threads in parallel. We have 6 of such micro engines in a chip. There is typically a 4 kilobyte of code size for micro engine, and all the code is stored on the on-chip memory. And then most importantly, we have a dual bank register architecture as shown over here, 64 registers in bank A and 64 registers in bank B. And the main purpose of these registers is to be able to get these operands in parallel so that the latency is minimized for real-time processing. Typically, these particular generation of network processors has 50 RISC instructions. All the ALU instructions finish in one cycle. Other instructions could take much longer, including hundreds of cycles for hashing, context switch, etc. And long memory latency using context switch to other threads is the mechanism that is used, and the latency of these could be about 20 cycles or so. So in other words, these threads execute in a round-robin manner. The threads keeps executing till they run into a memory operation, and in order to hide the latency, thread is descheduled when it runs into a memory operation, and the next thread is scheduled, and this process keeps continuing, and with a hope that once all these threads complete, the latency for the first thread would be done and the data will be in place, and that is how the latency is hidden by undertaking these round-robin scheduling on these threads. So when initially these IXP network processors came into being, code generation for these processors was in a very primitive stage, and the only way to write this code was to use microcode C, which was very close to assembly, and then one had to use the assembly tools to tune the code. So the way to write such code was to use predefined macros mostly, which will just translate directly into the machine code. This was a passive approach and would leave a lot of unresolved problems to the user or the programmer, such as handling not enough registers or register bank conflicts, or even writing very inefficient code even if it gets through the assembler. In particular, very few optimizations were done to make the code highly tuned, and so the class of applications that one could port on these network processors matching the line speeds was very limited. So in particular, the users had to use C compiler based assembly kind of tools. The users used to write this code in a subset of ANSI C. Moreover, they used to define the location of the variables such as DRAM, SRAM, scratchpad, registers, which had huge memory implications in terms of latencies. And having such a poorly written code could mean that you have a very inefficient execution because of very high latencies involved there. So this particular work solves a very important problem of register allocation for these network processors. In particular, it addresses how to assign the registers into different banks so as to produce a very highly optimized. So let us first understand this dual bank constraint for dual bank register allocation. So here is the restriction that is placed by the network processor ISA or instruction set architecture in terms of how each of the ALU instructions should look like. It prescribes that for those ALU instructions which have 2 operands, those 2 must come from different banks. In other words, if a ALU instruction has the need for 2 registers which it references to do certain processing, one of them should come from register bank A and the second one should come from register bank B. It cannot be that they belong to the same bank. Such an instruction is illegal. So you may ask, why such a restriction? The answer again is, we must be able to finish this instruction in a very fast manner at the line speeds. The clock frequency of IXPs is designed to match the gigabits which come at the Ethernet speeds, and therefore we must fetch these operands in parallel to be able to achieve the 1 cycle latency of all the ALU instructions. And so this design decision is a very critical decision which allows us to execute the ALU instruction in 1 cycle because both of its operands are fetched in parallel, and moreover to keep the clock cycle as short as possible because both operands are fetched in parallel from 2 different register banks. Again, the clock frequency that is designed to operate here is gigahertz, tens of gigahertz, and that is designed so that it matches the line frequency. So here is an example of how this should be done. So we have an ALU instruction here and we have 2 source operands A and B, and we are doing some addition there. So we got to produce one of the 2 schedules. Either we could have operand A in bank A and operand B in bank B, or we could have the reverse, that is operand A should be in bank B and operand B should be in bank A. So it got to be the top schedule or the bottom, but if it is neither one of them, then this instruction will be determined to be illegal by the execution unit. Let us look at the implications of this restriction through some simple examples now. Let's take a look at this example 1. What we have here is a very simple code excerpt in which we are adding A and B first, then next we are adding A and C, and finally we are adding B and C. Again, the restriction is both the operands must be in 2 different banks. So to make this particular example work, let us say we start by allocating A in bank A. That automatically means we must put B in bank B, otherwise this first operation will be illegal. The operands must come from 2 different banks. So A comes from bank A, B must come from bank B. Now, if we proceed further here and see what should be done to C, here is where we run into a problem. If we look at the second instruction, A is to be added with C, A plus C. A is in bank A, and so we can probably go ahead and say that since A was coming from bank A, the other operand C must come from a different bank, so we can say that C comes from bank B here. So we can go ahead and say that perhaps this comes from bank B, but then if we allocate C to bank B, let's see what happens further. We have B plus C, B is already in bank B, and so C cannot be in bank B, and that will make this particular last instruction as illegal instruction. In other words, if we respect the second instruction and allocate C in bank B, that violates the third instruction. And you can see vice versa, that if we satisfy the third instruction, we got to allocate C in bank A, and that will violate the second instruction because A is already in bank A. So this means that C is not allocatable in either bank under these particular restrictions. Here's the second example, which poses a different kind of problem. Again, we have some code excerpt here, which A is added to B, A is added to C, A is added to D, and so on. And in this particular case, we could do an allocation as follows. We could allocate small a in bank A, and given that A is combined with all the other things, we could go ahead and allocate B, C, and D in bank B. But then you can easily see here that we have only 1 operand in bank A and 3 operands in bank B, which means that the allocation is possible, but it puts a tremendous register pressure on bank B, and therefore we could soon run out of the 64 registers, and that could create an issue in terms of insufficient registers. So students, let's check our knowledge of register assignment in terms of the dual bank register allocation problem. What we have here is a nice simple statement. I would like you to fill it in with the right words to get the concept across. The statement is, the dual bank register allocation problem aims to reduce blank due to additional blank which can degrade performance and cause code explosion. Please go ahead and mark your answers now. The dual bank register allocation problem aims to reduce the overhead, the performance overhead, due to additional spill code which can degrade the performance and cause code growth. How? Because remember, if we run out of the total number of registers in one bank, and if we do not do this dual bank register allocation, then it will lead to a spill and that will degrade the performance. Second one is, if we are not allowed to keep copies, which is done by the dual bank register allocator, then there will be infeasible set of accesses, and we may have to forego doing any register allocation on them, and that will be a huge performance hit. So before we actually present an approach and the algorithm, let us present some definitions of how we model this particular problem. So we have a concept here of conflict edges. So we use the same standard representation that we use, which is interference graph, for modeling this problem, and we put additional edges on this interference graph called conflict edges. Now, what is really a conflict edge? The conflict edge indicates that if the two values are a part of a given instruction, such as an ALU instruction, they are in conflict. In other words, they must reside in two different banks. So for example, consider two source operands which are a part of some ALU instruction, and we want to indicate this by putting an edge between these two source operands, indicating that they must reside in two different banks. And that is what is a conflict edge is showing. So we build register conflict subgraph of an interference graph that shows these conflict relations, and it only has these conflict edges. Now let us consider those two examples that we saw earlier to show how they look in terms of this representation. So as you can see here, we have three different conflict edges, one between A and C, second between B and C, and third is between A and B, to indicate that at some point A and B were operands of some ALU instruction, so were B and C, and finally A and C were also operands of some ALU instruction at one point, and therefore they are in conflict. Similarly, for example 2, we get the register conflict graph as follows. We have ALU instructions that involve A and B, that is shown as an edge. Same is the case with A and C. Finally, similar is the case with A and D. You can see that we allocate these three in one bank and another one A in another bank, but that will make it imbalanced. Now before we proceed further, let us refresh our knowledge of interference graph, how to build those, and how to color those through a simple quiz. So what I'm asking you to do is, here is a simple program that I'm giving you, which is shown on the left hand side. I would like you to build this program into a control flow graph, then into the live ranges, and using the live ranges, generate an interference graph which is shown over here. We have shown the structure of this interference graph. All you need to do here is to fill in each one of these boxes here with what variables reside in these, so that we declare interference between the two. So for example, if this variable and this variable is interfering in terms of their live range, there is an edge. Remember and recall that relation. So go ahead now, generate the control flow graph and live ranges from this simple program, and then from there fill in this particular graph to indicate the interferences of live ranges. Go ahead and fill up your answers now. Now let us evaluate our answers for this simple quiz. The first thing that we are going to do is convert that program into a control flow graph, and this is how it should look. This is first basic block and so on, and these are the control edges that are being shown here. These are the different values which are being processed and so on. And what we also indicated here is the live ranges of different variables, which is between the definition point to the last use point of that particular variable. We have indicated different live ranges here. And then we are going to use a simple rule to declare interference between two values if they are simultaneously live at a given program point. So using this relationship, now we are going to start filling up these interference graph. But first, please take a look at the control flow graph and the live ranges that are found here and verify your answers. And now from this control flow graph and live ranges, we are going to fill up this particular graph, which is the interference graph. So I'm going to illustrate a few things here, and that way you can verify your answers. So we have here nodes F and A, which is corresponding to the live range A here, and a live range F, which is shown over here. Now you can see that at this program point, which is in between, both are simultaneously live, and therefore we have an interference edge between the two, which is over here. Similarly, we have interference between F and D because their live ranges do overlap, at least at this particular program point. And again, because of that, we do have an interference edge. And you can verify this to be true for even other edges, such as, for example, D and C. So we have a live range of D, which is going all the way here. And this is the live range of D, and this is the live range. So this is the whole thing is one web for D. And then the live range for C is going all the way from here to here. And therefore it is interfering over here between D and C. And therefore we have an edge between D and C here. So please go ahead and verify your answers for interference graph using these live ranges, and they're overlapping at least one program point. And then correspondingly, you should have an interference edge over here in the interference graph. Now the last part of this, we are going to refresh our knowledge about graph coloring. So given this interference graph that we got in the last step, I would like to ask you to color it with the minimum number of colors and put those colors in these boxes over here. Please go ahead and assume we have colors 1, 2, and 3, or any number that for that matter, which is the minimum such number, and use those to fill in these particular blanks in boxes on the right hand side. Please go ahead and mark the answers now. And the right answer in this particular case is, first and foremost, we need at least 3 colors. Why is that the case? Look at this particular part of the graph. This is a clique of size 3, which means each node which is a part of this clique needs a separate color. So we need at least 1, 2, and 3 colors. And then we use a simple rule that 2 neighbors should not get the same color if they have an edge which is connecting them. And by using this particular rule, we can see that this is a legal coloring that can take place on this graph. Now remember, this need not be the only type of coloring that could have taken place here. We definitely need minimum 3 colors. But we could have done a different coloring. For example, we could have started with 2 here, 1 there, 2 here, 1 here, and then correspondingly we could have shifted different colors here, maybe 2 here and 1 here, something like that, to make sure that it is consistent. So any such different combination of numbers is also a legal solution. It need not be a unique solution such as this. All those answers are also correct, as long as we have only 3 colors and no more. And second is 2 neighbors which have an edge cannot get the same color on both of the nodes. Now we'll refresh our knowledge of one more important concept, which is called as bipartite graph. So what is a bipartite graph? A bipartite graph is the one which we can partition into 2 disjoint sets in terms of its nodes, such that within each node we do not have an edge between 2 nodes which belong to one set, and all the edges are confined between the nodes which belong to 2 different sets. So here is our question, whether the shown graph here is bipartite or not. That is what we need to verify. So we are asking you to divide the graph into distinct subsets called A and B to satisfy this relation. So if we put 2 nodes in set A, they should not have an edge between them. And similar is the case with the 2 nodes that are put in set B. But all the edges should be covered for one node in A and second node in B. So The question is, can you label this particular graph accordingly so that it satisfies this bipartite relation? Please go ahead and mark your answers on this graph now. And now let us look at the solution of how this particular graph could be labeled. Again, a word of caution here. This is only one way of labeling it. It need not be the only way. There could be other ways which potentially could be labeled to decide this graph is bipartite. So all the different answers could be that they classify one set of nodes in A, second set of nodes in B. Again, no edges within two nodes belonging to A, and similar is the case with B, but all the edges are covered by the nodes which are in two different partitions. So if we color this particular node as A, then automatically we could color this as B. Again, its neighbor will color as B, and this particular neighbors of these B will be colored as A, and it satisfies the bipartition because again the edge belongs to nodes in two different partitions. And if we continue this, again all the neighbors of B should be in a different partition, so they are in A, and pick any vertex and make sure that is the case. B's neighbors again both are in A's, A's neighbors both are in B's, and so on. So since we are able to do such a labeling that when there is an edge between the two nodes, they are in two different partitions. Since we are able to do this and cover all the edges, no edge is left out here, this graph is a bipartite graph. Again, as I mentioned, we could do a different labeling. We'll start with maybe this node as B and these nodes as A's. If we flip A's and B's, that will also generate a legal solution to this labeling problem, and which will also verify that the graph is bipartite. So now we need to verify if the conflict graph that we have is bipartite or not. If it is, then we can allocate the whole set of nodes there in two different banks and will be done in terms of the register allocation. So here are some important results that we use for deciding these. RCG can be allocated in register banks provided it is bipartite and vice versa. And the most important result to decide whether RCG is bipartite is to have this particular important thing here, which is there cannot be any odd cycle in RCG. In other words, bipartite graphs are allowed to be cyclic, but there should not be any odd cycle. As long as there are only even cycles, we are fine in terms of bipartitioning that particular graph. Of course, the graphs which do not have any cycles are also bipartite. Simply by trying to pick them in odd-even fashion, we can put them into two different banks. But again, the important thing in the presence of cycle is that it must be an odd cycle. So with regard to this, let us see which of these examples could be fit into dual banks through bipartitioning. So here is a case of the register conflict graph that we had for example 1, and what is going on here is we do have a cycle, and this cycle is odd cycle. So if we do the allocation of this to bank A and that to bank B, we are faced with what to do with C. The question is it allocatable in two different banks as a bipartite graph? And the answer is obviously no. The reason is this cycle is odd length, and so therefore no matter what we do to this graph, we will never be able to allocate it in two banks without a conflict. Again, we look at the same graph, and even if we try to decide to switch the allocation of A and B, it doesn't help because inherently the problem is this graph is not embeddable in a bipartition in two different banks because of an odd cycle that is present here. Now you can see that for example 2, however, we do not have even a cycle, and so the embedding is very easy by taking all the edges and making sure that the nodes are in two different banks, and that's how we get a conflict-free allocation. However, it is imbalanced. So students, armed with our knowledge of what exactly is a bipartite graph, how certain cycles prevent the graph from being bipartite, and the knowledge of register allocation in terms of interference graphs and so on, we are now going to see how to do a register allocation which is sensitive to dual bank allocation problem using these abstractions. So when you carry out a dual bank register allocation, you can do it in many different ways depending on how it is phased ordered with the regular register allocation that we do. What is a phase order? Phase order means where exactly is it done in the compilation pass. Is it done before carrying out register allocation? Is it carried out during register allocation? Or is it carried out after the fact, after the registers are already allocated? So first approach could be that we do this dual bank assignment before we carry out actual register allocation. We call this as a pre-register allocation phase. So how do we do it? We do not have the register allocation done yet, but we do have the virtual registers allocated, an interference graph based on the virtual registers, and we work on that abstraction. And what is our goal? Our goal is to near balance the banks before handing it to the register allocation phase. So carry out this dual bank allocation or assignment on the virtual registers and make sure that each of the banks are almost balanced, and then give it to the register allocator. The second possibility, as I have mentioned in the last slide, was to do it after the fact. That first let the regular register allocation phase do its work and then follow it up by adjusting the allocated registers across two banks. So in this particular case, we actually work on the physical register conflict graph after the register allocation has been done. And the goal is again the same, to balance the two banks so that the number of spills are less. And last but not the least is to actually carry out the dual bank assignment during register allocation. And for this purpose, we work closely alongside of the actual register allocation phase. Now, having introduced these three different approaches, let us look at them one by one. So to begin with, we are going to look at the combined register allocation, that is how to do the register allocation and dual bank assignment together. And for that matter, we are going to use the famous register allocator that we have seen earlier, which is Briggs register allocation algorithm. So how do we modify the Briggs register allocation? So we modify the Briggs register allocator in this particular setting. Instead of one stack, we are going to maintain two stacks, one for each of the banks. And we are also going to make some changes in the simplify, select, and coalesce phases with regard to these dual bank conflicts. So in other words, we are going to take the Briggs register allocator during simplification, select, and coalesce phases. We are going to operate instead of one on two stacks by putting all the nodes of the interference graph on them, and then invoke the allocation phase, which is sensitive to these conflicts. Now, having discussed these three different approaches at a high level, we are going to refer you to the instructor's guide in the materials that has been given to you in terms of the paper on dual bank register allocation. We would like you to read this in depth in that particular paper. Before we conclude this lesson, we are going to attract your attention to two key optimizations which are at the heart of all of these techniques. So regardless of which approach we follow, we must make sure that the underlying conflict graph is bipartite, and so we must do certain transformations on them, and we are going to look at certain techniques which will achieve that. Again, there are three different approaches here: pre, during register allocation, and post register allocation. Please refer to the instructor's guide in those particular paper which is on dual bank register allocation, and please read the details of the algorithms and approaches from the paper. Let us continue this discussion in terms of how to make the graph bipartite if it already isn't. So detecting odd cycles in the graph is an NP-complete problem. We want to be able to achieve a high-quality approach which has a reasonable compilation time, and so we cannot really go for an NP-complete type of a solution. So we are going to look at two interesting observations here which will allow us to develop this detection as well as breaking the odd cycles. First observation is this, that breaking a shorter cycle may break longer cycles as well. So we want to detect the shorter cycles first and transform the program to break the longer underlying cycles which are sharing certain edges with these shorter cycles. And second is an empirical observation. Mostly these kind of cycles we have seen, especially the odd cycles, tend to be short on the register conflict graph. That is because many of these codes involve short loops, and the conflicts that take place in the register conflict graph tend to be due to those short loops with overlapping live ranges, and therefore these cycles also tend to be short. So students, before we get into the technique, let us look at a simple example that makes the point which I was mentioning earlier about odd cycles. In the following graph, put a check on the edge or edges that you think that should be broken to break all odd cycles. First of all, find out all odd cycles in these graphs. So then put a check mark against those edges which you think could be removed to break the cycles. And remember, there could be multiple choices here. So put a check mark against all the edges that you think are relevant here. Please go ahead and mark your answers now. Let us now check our answers. Which are the edges that should be removed to break all odd cycles? So the first answer is edge AB. First of all, how many odd cycles are there? There are two of those. One is ABE. This is one odd cycle of length 3. And the second odd cycle is ABCDE, which is of length 5. Now we can break both of them if we just remove an edge AB. Any other edge we remove might break one of them, but not the other. For example, if you remove this edge, it will break the bigger, longer cycle of 5, but it will not break the shorter cycle, which will remain in place. So edge AB is one right answer which will break both cycle 3 as well as cycle of length 5. But is that the only edge? Obviously not. What is the other edge that could be there? Let's look at it. And the second edge which you can remove from here independently could be AE. So instead of AB, we could also remove AE, and which will have exact same effect of breaking a shorter and the longer cycle of length 5. What we just showed is illustrated here. For example, if we decide to remove AB, it is going to break the cycle and make the graph look like this over here. In a similar way, the longer cycle of length 5 will be broken if we decide to remove AB, and it will look like this. By a similar argument, instead of AB, we could also remove just AE, which will break both cycle of 3 as well as 5 lengths. So in the last quiz, we saw that if we somehow detect and remove certain key edges for short cycles, it helps us to even break larger cycles that share some of the edges of the short cycles. But the real question is how to detect odd cycles in the first place. So we are going to look at an interesting algorithm here which makes use of certain characteristics of the graph. So what we first note here is something called as a node level, which is the shortest path length from the root to a given node. Next, we check if there is an edge between the nodes which have exact same shortest path to the root. So consider two nodes, node A and node B, and if that happen to be an edge between node A and B, and A and B are such that each one of them have a shortest path of length, say 4 to a root, then this particular edge between A and B is called as a parallel edge, and this parallel edge indicates the existence of odd cycles. So what we are going to do is build this shortest paths from the root to given nodes till a level of k to detect cycles up to 2k plus 1. Because again, remember, there could be k such nodes involved there, and they could form a cycle of all the nodes which are above them as well as which have the parallel nodes to them. And so we could use this to build the lengths to level k and then use those to detect the cycles of length 2k plus 1. So for example, consider a register conflict graph which looks like here, of consisting of 5 nodes, and we have several edges between respective nodes in this indicating register conflicts. In other words, B and E could not be simultaneously together in same bank, E and D could not be simultaneously together in the same bank, and so on, which is shown here as a register conflict graph. The conflict edge here means that they could not reside in the same bank because they could form the operands of the same instruction in the code that is generated. Now, having seen the register conflict graph, let us see how we can first build the breadth first hierarchy and then use the observation on the previous slide in terms of parallel edges to detect the odd cycles. So here is an example. So if we build the breadth first hierarchy here, in terms of finding out the depth of the node, selecting A as the root from it, we can see that we get here B and C at the level of 1, E and D at the level of 2 in terms of the length from A. Now we can see that we can detect B to C as a parallel edge because both have length of 1 from A and they have an edge across them. So that detects first odd cycle. Secondly, we can also detect an edge now between E and D which are at level 2, and because of this particular reason we also have a cycle here between A, B, E, D, C, A because of the parallel edge and E and D having the same level with regard to A. So here is a length of 5 cycle that we have detected, and here is a length of 3. Note that the length of the cycle that is detected here is 2k plus 1, where k is the level of this node. So for example, the level of E is 2 here, and the length of the cycle that is detected is 5, which is 2 times 2 plus 1, 2k plus 1. So students, having seen how to detect the odd cycles by using the breadth-first hierarchy, now let us look at techniques to break these cycles. We need to remove these conflict edges from our graph RCG, and one of the easiest ways to do it is to break the live ranges. So let us refer to this control flow graph in this example. You can see that we have an instruction here between A and B. So therefore, A and B have a conflict edge in the RCG. Similarly, A and C have a conflict edge in the RCG, and A and D have a conflict edge in the RCG. So we do have A and B sharing a conflict edge, A and C, and A and D sharing a conflict edge. But now what do? We decide to cut the live range at this particular line called X, and we have split the live range from A to A dash and A. Now A has a conflict with B, but A dash has a conflict with C, and A dash has a conflict with D. What happens when we split a live range at X? It removes certain edges from the RCG. If we continue the process and split one more edge of the control flow graph, the live range being split not only at X but also at Y and Z, and we call this live range as A dash, and then we call this live range as A double dash. Let's see what happens. Now we got three live ranges therefore, A, and we have an RCG here, edge between A and B. We'll have an RCG edge between A dash and C here, and we'll have another RCG edge between A double dash and D. Now because of the splitting in the control flow graph of live ranges, we have transformed the RCG. Now we have three different edges in the RCG with regard to three different live ranges. The first is between A and B, second is between A dash and C, and then the third one is between A double dash and D. And we have now removed the cycles which could have passed through BAC and BAD because of the removal of these kinds of edges. In other words, in the original graph, there could have been a cycle which is an odd cycle between BAC because of the two edges being present, and if there was an edge between BC, there would be an odd cycle. In a similar way, we could have had an odd cycle between BA and D because of the two edges that are sitting here between AB and AD, and if there were an edge between BD, that would form an odd cycle. And because of this transformation, now the edge AD has been removed, the edge AC has been removed, and therefore breaking these cycles, and therefore now we may not have any odd cycle which otherwise would be there before. If we just keep the live range breaking only at X, we can have an edge between A and B, but we still end up removing the edges between AC and AD, and any cycle which is incident like BAD could be removed because of this. So you can see that just by cutting only at X as well, we are also able to remove these two cycles. So either we can cut it at X, Y, and Z and transform the graph as in the previous slide, or the next alternative would be just to cut it at X and cut the live range only once and still be able to remove the cycle because the edges from AC and AD are removed. So the question is whether we should cut it like this only at X or whether we should cut it at Y and Z. Obviously, the answer is pretty simple. If we cut it at only X, the live range is cut only in two parts. If we cut at Y and Z, which was the case, this was Y, and this was Z, then you can see that the live range is cut in 3 parts, A dash, and this was A double dash. Now cutting a live range in multiple parts also incurs a cost, which is to move the data from one register to the other. For example, this A could be in one of the registers and A dash could be allocated in yet another register, and because of this we'll have to move the data from R1, which is given to A, for example, to R2, which is given to A dash. Moreover, we'll have to also move the data from R1 here to R3, which is given to A double dash. So in short, cutting the live range into unnecessary pieces also incurs a cost, and so if we can cut it minimally and get rid of the cycle, that is the best thing to do here. So the best way for this particular example to cut it is only to cut it at X, because then it leads to only 2 live ranges, A and A dash, and we will incur a move between A and A dash whose cost will be much smaller than cutting it into 3 pieces. So here is the big observation that we must keep it in mind when we do the transformation on the graph in the RCG by cutting the live ranges to break the cycles. Each cut point costs 1 additional move instruction to be inserted in the code from one register to the other. And since that cost is 1 move instruction, we must cut in as minimally as possible. So based on this, we develop an algorithm which minimally cuts the live ranges and also breaks the cycles maximally in the RCG. So here is the algorithm for cycle detection and breaking. We first start with the shortest cycle and then go for the longer ones. First, for a given cycle, all different live range splitting patterns that will break the cycle are identified and stored. We do an ordering on this particular procedure that if we end up breaking the longer cycle, it will not create a short cycle. So we could be non-monotonic here. And then amongst all different live range splitting patterns, we identify the ones which has the shortest or the least cost and split that particular live range and break the respective cycles. So here is the overall algorithm. First, we want to store all live range splitting patterns to be stored in a particular set, and that is for the shortest odd cycle, which is length of 1. And then we start the procedure here. We build the hierarchy. We find out all odd cycles of length k, and k is smallest, as you can see here. And as long as we have some cycles detected there, we find a pattern which breaks that particular cycle with the minimal cost, so that the ratio of number of cycles broken to the unit cost that we pay for breaking that cycle is maximal. Remember, this ratio is m divided by w. That is, by introducing w cost in terms of moves, how many cycles we can break, and whichever has the highest such ratio is what is selected. We go ahead and break this and keep breaking cycles at that particular k over here. When this becomes empty, next we go to the next odd cycle by incrementing k by 2, and we repeat this particular procedure, and therefore systematically we'll remove the cycles by introducing the live range splitting. We start with the least length cycles, odd cycles, and we proceed towards longer and longer cycles. This is with a hope that, again, by breaking a shorter cycle, we would have already broken a longer cycle, and therefore we have lesser work to do for breaking longer cycles. As mentioned earlier, again, using this approach of breaking the cycles, we simplify the RCG and give the modified RCG to either a pre-register allocation phase or a post-register one, or in some cases, we are doing this during the register allocation by coupling it with the Briggs allocator. Again, refer for the details of all the algorithms and integration of this approach with 3 different register allocation strategies. Please refer to the instructor's notes in the instructor's manual. Let us test our knowledge of the trade-offs that are involved in cycle breaking with regard to the additional costs that we incur through a simple quiz. Please select the true statements and put a check mark against them. Multiple statements could be true, so I'm going to read those out to you. The first statement is the odd cycle optimization to break odd cycles can have different costs. Is it true or not? The second one is odd cycle optimization is applicable to pre-array bank assignments only. And then the third one is the odd cycle optimization requires an additional registers but this overhead is offset by performance improvement. Please mark all the statements that you think are true. Go ahead and mark your answers now. And let us come back and now look at the answers to the quiz. So which statement is really true, or which statements could be true here? The odd cycle optimization to break odd cycles can have different costs. This statement is true. We've seen an example wherein if we cut the live range in different ways, it could still break the cycles, but it could incur maybe more move instructions in those cases, such as breaking the cycle at Y and Z costs more than just breaking it at X. The second and third statements are not true. The optimization could be applied to any approach, not just pre-RA, because once the graph is simplified, it is up to the allocator what to do with it. So it is in a way decoupled from the allocator. And the odd cycle optimization required additional registers. That is also not true, because when we break we could simply put a move statement, but it doesn't increase the register pressure. It does not increase or cost more in terms of registers here. It costs in terms of a move instruction. Now we are going to touch upon just a few important things, and again refer you to the paper which is in the instructor's manual, which has all the details. For post-RA approaches, we actually make a use of rematerialization in place exchange to guarantee cycle breaking. That way we do not induce any more cycles. So our other premier objective here is to keep the two banks almost balanced, and so when there are no edges between certain parts of RCG, which are the disconnected components, we just assign them randomly to keep those banks balanced. We also have in this paper, in details it is discussed how we do some in-place exchange to keep the two banks balanced, to move an operand from one bank to the other and swap it with another operand, for example. And then finally we have some enabling techniques which make RCG more viable for live range splitting and odd cycle breaking. Again, please refer for all these to the paper in the instructor's materials. Let us now look at certain benchmark results. These are the different benchmarks from NetBench which have been used here for evaluating these techniques. These are the code sizes in terms of number of instructions, number of live ranges, number of interference edges, and number of conflict edges. So you can see that a fair amount of conflicts exist in RCG, and therefore a fair amount of cycles could also result before the technique can be useful here. So here is a comparison of these techniques in terms of extra number of moves that are inserted here, and as you can see here, the post-RA technique is a little bit more worse than pre-RA and combined approaches. The combined approaches tend to have less number of moves inserted, least number of moves which are inserted over here. However, if you look at the number of spills that are resulting, the post-RA is the best. The main reason why post-RA is much better than the other approaches is that the baseline register allocator is optimal here. It has removed all the spill it can, and then it just remains a problem of allocating the register to different banks so that you do not introduce the spills because of imbalance. And as you can see here, that is the case, and so the number of spills that are introduced because of bank allocation inefficiency is very small. Whereas in the other cases, the spills could be a combined effect of not such a great register allocator or not an optimal register allocator, and on top of that, additional spills due to inability to put these operands in two distinct banks. So that's why some of these numbers look high. It is because of the fact that the underlying register allocation may be less than optimal as against this particular case. Let us look at the number of cycles and overall performance result because of this. Again, as you can see here, post-RA tends to be the best technique because of baseline register allocator and less number of spills. So over pre-register allocation, the post has almost 9% benefit, the lowest being about 5%. And over the combined one, the post still has about 5% benefit over here. So what is the conclusion of this particular paper? The conclusion of this paper is that let us start with the optimal register allocator. Let us get rid of all the spills we can and then place the different registers into different banks, trying to use our method that would yield the best code, or approaches which either blend it in during register allocator, which is non-optimal, or doing it as a simply before even register allocator is applied, as in pre-step here. So get rid of the spills as much as you can and then do the placement is the best approach. That's why the post-RA method is the best method over here, which is advocated for a practical usage here. The post-RA also has some costs such as moves, but those moves are carefully kept minimum by the approach, and so combining an optimal register allocator with another approach which breaks the cycle, which least number of moves inserted, which is shown here, works or happens to be the best. For details of these benchmarks, results, their discussion, analysis of different approaches and their comparisons, again please refer to the paper in the instructor's materials. We learned some valuable lessons about register bank conflicts. What did we discover? We discovered that the post-register allocation approaches are the best in reducing spills, but they come at the cost of code expansion. In general, it is good to do register allocation without the bank constraints, treating registers as a whole, and then do the bank assignments to minimize the spills.